Welcome to our lecture on 7.1, which is going to be on linear system of equations, and we're going to throw in some new for us nonlinear system of equations. Now, right off the bat, you're probably looking at number one and you're thinking, wow, it's pretty simple and it's not going to be any different on those base cases. So for 7.1, the key feature is we're doing every single one of these systems with substitution. So we're not using that elimination method where you get things to cancel out. It's solve for one variable, substitute in, solve for the rest, and then back solve to solve your system. So let's just see an example real fast with number one. So number one, you're always going to have the two systems in this case to choose from, or the two equations. You always want to pick the simpler of the two to start off your substitution. So by that, I mean we have no coefficients on either variable for the first equation, but we're stuck with this 5 and 3 on the second, which means if I try to solve for the x or y, I have to divide that off. Make it easy on yourself. Start with whichever equation is more simple. Well, in this case, I'm going to solve for, say, x, and we'll substitute x into the second equation. All we got to do is add that y over, and conveniently for us, we just get that x is equal to y. Now we do that substitution. So working with this second equation, now we have 5 times whatever x is, minus 3y equals 6. And we just saw, well, x is y, so you just make that nice little substitution. From there, just a simple equation. 5y minus 3y, we get 2y is equal to 6. Divide by y. Sorry, divide by 2, we get that y is equal to 3. So there's our substitution. We then need to back solve into that first equation we solved for to get our other variable. So how are we going to get x? X is equal to, well, we know y is 3. And of course, in this one, it's not too bad, right? We just get right away that x is 3. We don't have to solve anymore. And then the key piece on ending every single one of these systems is that the system is two, in this case, 2 lines, and it's where they intersect is this solution, so we want that as an ordered pair. So our final answers should be the ordered pair that is the solution to that system. So right off the bat, we've done substitution all year, so that part's really nothing too crazy. It will sometimes be more of the setup. So as we move on to number 2, I'm going to help you get started on the setup, and then I'll give you guys a minute to pause and work out solving that system. So let's start with the setup of number 2. So we have a total of $25,000 being invested into 2 funds, and each fund is going to pay out separate interest. One is going to pay out 6.5, and then the other one's going to pay out 8.5%. The total interest we're going to make off this investment is $2,000. And then we just want to know how much is invested at each rate. So we want to know, our variables are how much was originally invested. So how much was originally invested into, say, the first fund, and how much was originally invested into that second fund. So the fund paying out 6.5 and the other one paying out 8.5. So let's take a look at what we can find for our 2 different equations. So right off the bat, we know how much was invested, 25,000. So between our 2 funds, we know that total investment has to be 25,000. So the nice thing about that is we not only create an equation, but we've pulled a piece of this application out of the problem. So we don't really need to think about that when we create our other equations. So that 25,000 is handled. We now need to find a way to tie in the 2,000 and our 2%. Well, we do know that some amount of this first fund added to some amount of that second fund is going to ultimately give us $2,000 interest. Well, how much of each of those funds? That's where that percent comes in. So we have 6.5% of, we'll say the first fund, X for us. Again, this is going to be a decimal, however, so we got to bump that over 2 spots. So 0.065 times that first fund, that's our interest from that one. And then similarly with our interest from the second one, 0.085 times however much we invested into that second one. So this is kind of a good strategy for building our systems. Give it a read through, but do what you can once you've used a piece of information to kind of remove it from it. You whether you color coding or underlining, that way you're only looking at the key information that you need. So we got our system. I'm gonna have you guys give it a pause and give it a solve using that method of substitution. So hopefully you gave that a pause, and as we come back, take a look at it. So right off the bat, I looked at that top equation. I think that's a little more simple. If I just subtract the y over, I have my x. Now, a trick that's really helpful when dealing with systems, especially when your coefficients aren't as user-friendly, is you can change it. So if we multiply both sides of this by 100, we end up dealing with coefficients of 6.5, which is just a little bit easier than I think dealing with something into the, say, thousands place over here. So that's what I did. You don't have to do that at all. Obviously, we have calculators, right? So it's not that big a deal. For myself, I just rather deal with as normal integers if I can in that direction, such as these. So once I have my system that I want to work with, I substitute what x is into this x. So we have that happening right here, that 25,000 minus y. And we're just plugging along, right? Solving that equation. We get y, for us, we noted is the one at 8.5%, is ultimately 18,750 of our 25,000 was invested into that. Well, once you get one value, you plug it in to find the other, right? So we have that our x was that 25,000 minus whatever y is, just that difference. And we get that x is 6,250. So that 6,250 was invested at our lower percent, at about 18,000 at our higher percent. And in this case, because it's an application, it's also kind of nice to give it some context, but I would just get into the habit of writing it down always as an ordered pair. So technically, none of this is new. This is from way back Algebra 1. Let's take a look at some nonlinear systems, however, and see how that changes it up. Coming on that second page, we have two different versions we're going to do dealing with nonlinear systems. One that's going to give us two solutions out of it, and then one that's going to give us no real solution out of it. Now, if we look quickly, we're dealing with something quadratic and something linear, something quadratic, something linear. And if you kind of look at the bottom of this page, it shows you the examples of what's happening there. Well, if you have, say, a parabola and a line, what can happen? Well, it can intersect it at 2 points. It could intersect it at the tangent point, just at 1 point on the edge, or they could just not intersect at all. So we're going to be looking at either of these cases at the bottom. So we'll do number 3 together, and then I'll give you guys a chance at number 4, finding the no real solutions. So nothing different than we did before. We're going to take one of these, solve for whatever variable is easiest, substitute it into the other equation. So right off the bat, I want to deal with the non-quadratic stuff first. And this y is already by itself, so I'm just going to take this and solve for y. So we get y is equal to 2x plus 5. So we got y. We now need to substitute it in to this quadratic case down below. So we got the x squared. We have minus whatever y is. So that's our 2x plus 5. We got that plus 3x, and that's equal to 1. So we're going to clean this up, right? We're going to distribute this negative. We're going to combine some like terms with our x's, and then I'm going to bring this 1 over as well. Reminder, it's something quadratic, right? So we want to set it equal to 0. When we do that, we end up with x squared plus x minus 6 equals 0. And where in the other problems, right, we would solve, we get some value for, say, x. We plug it in, we have something quadratic, which means we could have up to 2 solutions. In this case, you know to expect 2 different solutions. So we can factor this. We factor this, we get x plus 3, x minus 2. So then we get 2 cases. We get the case where x is negative 3 and the case where x is 2. So what do we do from here? We look at both cases. We take this x is negative 3 and we plug it in to the original. So we get the y that pairs with that negative 3. And then we just do the same thing down here for the x being equal to 2. So it's still that same original one we solved for, 2 times 2 plus 5. Well, for the first, we end up with just y is equal to negative 1. For the second, we end up with y is equal to 9. And then our solution as a whole, the entire answer, is now 2 ordered pairs for us. We have the first, which is negative 3 comma negative 1. And then we have the second, which is that 2 comma 9. So same strategy. We're isolating the variable on our simpler equation. We substitute into the other. Then whatever methods we had for solving, like solving quadratics, we're just using exactly that. If it breaks into two cases, we just look at each one separately. Now you're going to do something extremely similar to number 4. I will give you the hint for number 4. It's not factorable, so you will use quadratic formula here. So my hint to you number 4 is towards the end, when we get about this point, instead of factoring, you'll use quadratic formula, and that's where we can really talk about this idea of no real solution versus just no solution at all. So coming back from working on that number 4, right? First thing we do, we solve for the simpler variable in the simpler equation. So that's our linear equation, and this y is more or less by itself, so it's easy to solve for that. So then we solve for y, and then when we solve for y, we substitute it into our quadratic. Now in this one, however, that y term is also squared, so we need to make sure that we square this and then simplify. So make sure we pay attention to little details like that that come with any of our nonlinear systems. When you do that, you end up with this quadratic right here. Now, myself personally, I hate negatives. I've said it all year long. They're the toughest thing to deal with. This is quadratic though, and it's set equal to 0. We can just multiply through a negative 1 and change the sign on all three of those. That makes it a lot easier when you're dealing with quadratic or really anything, and then it kind of removes an extra level of confusion or error that we might have. So we do quadratic. We have our a is 2, b is 8, and c is 9. Plug it into quadratic formula. Everything's looking great until we end up with this negative 8 on the inside of that square root. Now, we've dealt with complex numbers. We know we could start dealing with I, right? And then go from there and simplify and look at the two different versions. We're looking specifically for real solutions with these systems because we're looking at it ultimately graphically, and for us, that's on the real plane. So because of that, that forces it to be a complex number. So it's not an element, it's not a number or a piece of the real numbers, in which case we're done. We don't dive into the complex portion necessarily right now, and we end up with no real solution. So again, what's happening in those two problems? For number 3 up there, we have this intersection of something linear and quadratic, and it hits it twice. And then for number 4, we have this set up, again, something linear, something quadratic. However, because of the quadratic nature of that parabola, it allows for it to not intersect at all. Now, again, when you dive into complex numbers more in the future in your math careers, you'll see that there's solutions to this and how does it look like, but for now, we're just touching on the real cases. So we have a couple applications coming up, but first we're going to see how we can find these solutions on a graphing calc as well. Coming onto that third page, the number 5 is going to be dealing with a graphing calc. If you don't have one, you can hop on the Desmos. It'll help you with doing the same process, except for Desmos will do some of it automatically for you. So to use a graphing calc, to graph any functions really, the issue is that we need to have our dependent variable. It needs to be isolated. So in this case, the y is isolated for the first one, so we're good to go, 3 minus log x. But we can't necessarily type in negative 2x plus y equals 1. We have to have the dependent isolated. So we just need to make a quick little fix on that, just like we would normally do with solving these. We're just going to isolate that variable. So we have y is equal to 2x plus 1. So now it's in a form we can use. So we get that 2x plus 1. And then if you're on Desmos and you plug these in, Desmos will most likely not only automatically graph them, but it'll probably show you the intersection point, which is the solution to the system. But if you're in the graphing calc, here are our steps. First, we go to graph, take a look at it. So this is just a standard graph, 10 by 10, and it looks like it's intersecting up here in quadrant 1, and you can use your trace tool, and you can try to get as close as you can, but the nice thing about it is we just have a tool that will find that point for us. So on the graphic calc, if you go to second trace, where it says calc, and no shocker, down to number 5, intersect, all you have to do is you have to pick the first curve, which it'll already be on, then just move over to select the second curve, hit enter. Oop, get that mixed up. And then you just need to get roughly in that area for a guess. That way the calculator knows where to look. And after you do that, it spits out that solution of that system for you. So our solution here is 1, 3. Now the nice thing is, yes, if you had a midterm, you need to show the work and the steps and all that, and you want to be sure that you've done the correct work, you can always check it graphically with that graphing calculator. So it's a nice little kind of double check at the end of your work. So those are kind of our basics of solving the systems. We're going to look at 2 applications. So moving on to number 6, just like on the pages before when we had an application, it's always going to be that setup that's the tough piece, the solving of the systems you've done before. We're going to be practicing again, so that won't be too bad. So again, here we'll focus on the setup, and then on the next page, you can kind of use that application and give that last one a shot. So break-even analysis. So we're talking about cost, we're talking about business. So when we're talking about cost of a business usually comes in 2 different pieces. You have your initial cost to kind of get things rolling. And then if you're producing something, it's how much per unit, how much per pair of shoes, per shirt, whatever it might be. That total cost you put in is going to be the total you kind of owe. Revenue is how much you're pulling in as a whole. So it's how much you're making. And then finally, we're going to have a conversation at the end of this one about profit, which is the difference of these 2. You know, it's the how much you've totally made, removing how much you got to spend on the cost, and that gives you our revenue. So we're going to be building up the first system, dealing with revenue and cost, because we want to know when are these 2 going to be even, because that's our break-even point. In a business, that's when you aren't making any money yet, but you're not losing any money anymore. So it's that point where things are going to shift for you. So first we have our cost. Again, we said cost comes in 2 different portions. You have your initial cost, so your initial investment. And then you have the cost it makes to produce. In this case, producing is going to be $12 per item in order to make it. So that cost is that initial $300,000 you have, well, plus an extra $12 per unit. And then revenue, how much we make, well, there's not a big lump sum for your revenue. It's just making money off each of those products. So per product for our revenue, we're making $70 per that unit for however many units we sell. So there's our system. Not too bad, right? We have cost is that 300,000 plus 12x, 12 times each unit. The revenue is $70 per unit. So the first thing you guys are going to do is find that break-even point. So from this system, we want to know when are these 2 going to be equal. So you guys will give it a pause and give that a shot. And then at the end of that, we want to find out profit. So we ultimately want profit, which is your total revenue, so how much you're making, minus your cost, how much you have to spend. That's going to give you that total profit. And in the second part of this problem, we want to know, okay, well, when are we going to get a profit of $1 million? Well, we can do that by finding the difference of our revenue and cost. So I'm going to have you guys give it a pause and do what you can to kind of interpret what it's asking for, right? The break even when cost and revenue are equal, and then use those 2 from that system to find when we're going to hit a profit of $1 million. So as we come back, the first part of that problem, we just want to find the break-even point. So when our cost, that 300,000 plus 12x, is equal to that revenue, 70x. So we just get to set those equal. And then we're just solving for x. And we end up with x being about a little over 5,000 units need to be sold, made and sold, in order to break even. Now, we didn't need to take this and then plug it into the system again to find other values. So that's a nice thing, especially with this applications. Typically, you're setting up a system, but you're not going to necessarily use it the exact same way you would before, where you must find every little piece. We can ask different questions about those systems. For example, when it comes down to finding the profit, we wanted the profit to be $1 million. Well, it's just the revenue, so our 70x, minus our cost, that 300,000 plus 12x. And then again, it's not too bad, right? You're just solving that equation. You're going to distribute that negative. You're going to get $1 million is going to be equal to 58x minus 300,000. And you'll eventually solve for x. In this case, when you do a little over 22,000 units made and sold, that's when you're going to hit that $1 million profit mark. So keep in mind when doing applications, it's not always build the system, solve for one, plug in for the other. We can ask some other questions about it. And we're going to see that with a lot. So as said on the last page, when we have a system, we may not just be solving for every little detail of it. So it's important to make sure you read in the question, see what they're looking for. And we're going to see that it's less work than we think in this last problem. So we have 2 new movies that came out, an animated movie and a horror movie, and they're released in the same week. So in the first 8 weeks, the weekly sales, the ticket sales, S, so that's, we already are given the system of each, is decreased over time, right? Because people aren't going to see it as much, but it gives us that model. So we have one of our movies represented in the top equation, one in the bottom, and that's an equation representing the total sales in those first few weeks. Now, here's the important part. We're not just solving for one, substitute in, solve for the other, get that ordered pair. All it's asking for based on this model is in what weeks were the sales equal. So just like the last one, when cost and revenue were equal, just that first little equality we had to build is all we're doing here. So we want to know in what week, and for us, X is representing our weeks. Are the 2 movies equal? Well, we can just set the sales equal to each other and find out, well, when does that happen? So we have 108 minus 9.4x. That's equal to 16 plus 9x. And we're just solving from x for there. So we end up with 18.4x is equal to 92. And then finally, we get x is 5. So that tells us at 5 weeks, the total sales are equal. Now, I think a lot of us might look at that and go, oh, that's it? That's kind of too easy. But that's the point I want to bring to your attention is when you are doing some of these applications, it could be just as easy as this. Now, we could build on this. We could find out, okay, at what week will it have a specific sale price? We could find out what that sale price was when they're equal, but it's just looking for that first value of x when they're equal. So keep that in mind when you're doing the applications. Take the extra 2 seconds to reread it to make sure you're not doing extra work if you don't need to. So that wraps up our 7.1. Again, everything with substitution. In 7.2, we'll hit that topic.